Welcome! Today we'll explore how probability underpins data science, guiding decisions and predictions in a world of uncertainty. Probability quantifies how likely an event is to occur, ranging from impossible to certain. In data science, it replaces guesswork with measurable uncertainty. For instance, it helps predict subscription cancellations or spam emails. A value closer to 1 indicates higher likelihood, while closer to 0 suggests less likelihood. Understanding this is foundational for predictive models. Understanding probability requires knowing key terms like experiment, outcome, and sample space. An experiment, like rolling a die, produces outcomes. The sample space includes all possible outcomes, such as numbers on a die. Events are sets of outcomes, like rolling an even number. These terms translate real-world problems into data science solutions. Calculating probability involves dividing favorable outcomes by total possible outcomes. For example, the probability of drawing a heart from a deck is 1/4. Simple events have one outcome, like rolling a 3. Compound events have multiple outcomes, like rolling an odd number. Understanding these basics is crucial for data analysis. The complement of an event is the probability it does not happen. If rolling an even number has a probability of 1/2, not rolling an even number is also 1/2. Complements are useful in binary classification, like fraud detection. This concept helps in understanding mutually exclusive events. It's a vital tool in probability calculations. The addition rule calculates the probability of one event or another occurring. For mutually exclusive events, probabilities are simply added. For non-mutually exclusive events, overlapping probabilities are subtracted. This prevents double counting. Understanding this rule is essential for accurate probability assessments. It's widely used in data science applications. The multiplication rule finds the probability of two events happening together. Independent events do not affect each other's probabilities. Dependent events influence one another, altering probabilities. For independent events, probabilities are multiplied directly. For dependent events, conditional probabilities are used. This rule is crucial for modeling complex data interactions. Conditional probability measures an event's likelihood given another event has occurred. It's calculated by dividing the probability of both events by the probability of the given event. This concept is pivotal in data science applications like fraud detection. Understanding conditional relationships enhances model accuracy. It's a cornerstone of advanced probability theory. Probability distributions show how probabilities are assigned across outcomes. Discrete distributions handle countable outcomes, like die rolls. Continuous distributions manage ranges, like height or temperature. Understanding distributions aids in interpreting data patterns. It's the starting point for exploring more complex statistical models. Mastering this is vital for data analysis. Probability underpins many data science models, like classification or risk analysis. Models rarely state certainties, instead providing probabilities. This approach is crucial for decision-making processes. Understanding probability ensures robust model foundations. It's essential for practical applications like spam detection or medical diagnosis. Learners often confuse probability with possibility, forgetting it ranges between 0 and 1. They may mix up independent and dependent events, or add probabilities that should be multiplied. Overlooking overlaps in non-mutually exclusive events is common. Misunderstanding conditional probability is also frequent. Addressing these errors is key to mastering probability. Achieving learning outcomes involves defining core probability terms accurately. Learners should identify outcomes, events, and sample spaces correctly. Calculating simple probabilities and explaining rules like complements is essential. Distinguishing between independent and dependent events shows understanding. Connecting probability to data science use cases indicates mastery. This is a main callout for this scene. It brings into focus the core idea being discussed. The central limit theorem explains how sample data behaves with repeated sampling. It states that sample means form a normal distribution as sample size grows. This theorem is crucial for making population inferences from samples. It supports statistical methods even with non-normally distributed raw data. Understanding this is foundational for data analysis. Probability theory is foundational for data science, supporting models and predictions. Understanding core principles like probability measures, rules, and distributions is essential. Mastery of these concepts enables effective, data-driven decision-making. The central limit theorem ensures reliable analysis even with samples. Probability remains a cornerstone of statistical reasoning. Feel free to reach out on WhatsApp at 074-8436-1688 if you have questions. Our team will be delighted to help. Thank you, and see you at the next session.